Let's get it. I hope y'all doing good. You know, been working so much, trying to post some more videos of this. As I study for the PE chemical exam. So, all right, so we got a problem here. Let me see. All right, and let me read the problem statement. Water will be pumped from Devil's Lake. Something I just came up with. It probably is a Devil's Lake. I really haven't seen if there's a Devil's Lake in the United States, but I think it for for some reason I don't know why I thought about it. It probably is in the United States. To the top of the nearby mountain through a 6-inch Schedule 120 pipe at an average velocity of 12 feet per second, the water discharges into the atmosphere at a level of 3,000 feet. So, at the top of the mountain, there's a discharge point of 3,000 feet above the lake. The pipe is 4,500 feet long. If the overall efficiency of the pump and the motor is 70%, determine the cost of power to pump this water if the cost of electricity is 4 cents per kilowatt hour. All right. And then I'll take you over to the problem. All right, so we here at the problem and water. We got so I just wrote out all that we need. So it's water at 60 degrees Fahrenheit, and so we know the piping is a 6-inch Schedule 40. So I looked it up online. So the inside diameter is 5.5 inches, uh, roughly. So it's I mean basically it's 5.501 inches, and we got the velocity, average velocity across this whole thing is 12 feet per second. So, um, and so that's the average because we know velocity decreases um, as you go further along the pipe. So you just take the average of those to get 12 feet per second. I don't know which average, but it is an average. And so, we got this. I don't know what this symbol is right here. I think it's new, or it can just be straight in sub P. And that's 0.07. That's the efficiency. And hopefully these look familiar to you. As we go along, you'll see why I use these symbols. L, length of the pipe, 4,500 feet. And then ZB, the height, discharge point at 3,000 feet. Now, let's get into it. So, this is what I done. Solve for a solution. If first let me give you. Well, it's probably too late now to tell you to solve the problem yourself. So I might just put something in the front uh, while we was over there reading the problem statements, saying solve it on your own first. So I'll just edit that in eventually. All right, so I calculate the density at 60 degrees Fahrenheit, and which I got from this book called Unit Operations of Chemical Engineering. That density is 62.37 pound mass per feet cube, and then I looked it up the viscosity in the appendix of that same book, and it came out to be 1.129 centipoise times 6.72 pound mass per feet cube. Per feet per second. And so, multiply that. That'll give me 7.59 times 10 to the negative 4 pound mass per feet second. So, the Reynolds number. So, the Reynolds number can be used just to describe the characteristics of the fluid flow. I think it's the ratio of the external forces to the internal forces. So basically, like driving force over the resistance type of thing. The viscosity will resist the fluid from, you know, from from moving. You know what I'm saying? Uh, so uh, so basically, so 62.37 pound mass per feet cubed times 12 feet per second times the diameter. You gotta divide that by 12 to make it into feet, and then divide by the viscosity. And so I showed the units, so you see you can cross them out, and then it'll be unitless as the answer. So the Renaissance came to be pretty huge, 40, 451,628, uh, and then we know that's going to be highly turbulent. And so out of that same book, there's an equation for a range uh, that you can solve for F, the friction factor. And so that's what I done here. Plug in the Reynolds number, or you can use the what is that? I think in y'all courses y'all probably use the Kármán-Vaughan equation. I didn't put that in there because it takes too much work. I think von Karman or Kármán-Vaughan, whatever it's called, but uh, but that'll give you a more accurate answer than what I have here. So if you use the Kármán-Vaughan equation, I think the percent error is 2% from the Moody chart. You can also use the Moody chart um, for this. If you put it, well, not really. I guess you need the roughness of it, uh, and it didn't tell us what type of pipe. You can just get, I guess, assume a steel pipe. But anyway, so I got a friction factor of 0.0033. All right, and now it's time for the equation that I was talking to you about previously. The mechanical energy balance, or the Bernoulli equation. It doesn't matter what you use, um, really. But right here, I try to turn into a. Well, at first I was going to use the mechanical energy balance, but then I decided, why not just use Bernoulli? So, um, and I use the foot form. There's an energy form, there's a pressure form, uh, energy form, and the feet form, head form, called head form. And I use the head form on this one, it looks like. And so, you know that this is at atmospheric pressure at this point, open lake at the top, it discharges atmospheric, so we can cross that out. And then we know at this point here, we know we know that there's no change in the change in diameter throughout the pipe. So that's that goes to zero. And now we left with the height and then the uh, friction losses, and then the work of the pump. So we know that the friction loss is 4FL over D. You'll hear that a lot in your courses. I just remember that at the top of my head. 4FL over D, and then times the velocity head. So we put all those up in there. Yes, sir. Yes, sir. Yes, sir. And that's the diameter right here. Once you divide the inches by 12, that's the diameter. We did all that, so you can see cross out the units. We get 2,900 feet. And here, that's why I like using the head form, because 0 minus 3,000 feet. That's negative 3,000. All right. So now we can calculate the work of the pump by using this equation, Bernoulli equation, 3,000 feet plus 2,900 feet. Divide that by 0.7 is 84. 8,429 feet. Now, now we gotta actually, in order to calculate power, now it would have been easy to calculate power if we used the energy form of the Bernoulli equation or the mechanical energy equation, whatever, balance. But I guess this is good practice to show to help you convert from the head form to the energy form. So you multiply that by uh, the head form by 32.2 feet per second and divide that by G sub C, 32.174 pound mass per foot per pound force per second squared. And so, doing all that, we give you 8,436 pound force foot per pound mass. So, energy form. And now we're gonna go to the second page. Now, you need the mass flow rate. So we know the density, we know the velocity, and then we know the diameter. You can actually calculate the mass flow rate. So 62.37 pound mass per feet cubed times the area, a circular pipe, times 12 feet per second. They give you 123 pound mass per second. And so now, calculating power. So power is going to be your mass flow rate times the work of your pump, and then you got to convert it to kilowatts per hour. All right. So 123 pound mass per second times 8,436 pound force per foot per pound mass times 0.746 kilowatt per horsepower. Yeah, that's the conversion. Times 3,600 seconds per hour divided by 550 pound force per foot per horsepower. So do across all your units, you get kilowatt per hour. So you get this huge power right here. 5,066,643 kilowatts per hour. So, man, this is going to be pretty expensive. So, well, we'll see. So the cost of that of electricity of that utility will be 0.04 cents per kilowatt hour, which basically is the the wattage per hour, the kilowatts per hour, same thing, times our power, kilowatt per hour. So that gives me the cost to be $202,066. I wish I had that in my bank account. And so I put a little thought question here as well. What other costs does this project needs to be considered? And so I was like, the cost of the pipe, the cost of the pump, and then operation and maintenance costs. If you can think of any other, just put it down in the comment section. So, yeah, so if you like this video, please give it a thumbs up. And just tell me what you like about it in the comment section. If you like to see more fluids, me doing fluid flow problems as I study for the PE exam, just let me know. All right. So, yeah, I'm about to end the video. See y'all in the next problem. Bye bye.